All right, so the last step of the data understanding phase, or the last task that we haven't been through yet, is to detect and understand the relationships between pairs of variables. Not necessarily all pairs of variables, well, in some cases, but mostly we're looking for the relationships between the label and all features, or if we have more than one candidate label, each of the candidate labels and the features. So we don't necessarily need to have the same level of depth of understanding of the relationship between all features. We do need to understand that for an assumption called multicollinearity, which we'll cover later in the book. But for right now, we're going to focus on the relationships between a single label, and we're going to use the same data set that we started on before. This is the insurance data set right here. So our label is charges, and we want to understand what the effect is of each one of these features on the labeled charges. So there's a term we use for this called effect size. So effect size, think of this as the relationship. The stronger the relationship, the stronger or the larger the effect size. And when we have a lot of features, in this case we only have 6, so it's really easy just to go through and test all of them, but sometimes we have hundreds, perhaps even thousands of features. In that case, this step is really important because we want to find just those handful of features that have the largest effect size. And by going through and testing each of them out one by one in a bivariate relationship during the data understanding phase, we can save ourselves some time or provide some more direction during the modeling phase a little later. So for now, let's dig into bivariate relationships or effect size. Now, to do this, we need to understand the data types because not all data is the same. The appropriate analyses for each type of data are different. So this table is a good summary, and this is something there to memorize or just commit to memory. When we have 2 numeric variables, the most common effect size statistic is a Pearson correlation. Now there are dozens, many dozens of versions of this that depend upon a variety of, for example, if some assumptions aren't met, there's better versions. There's a Kendall correlation, a Spearman correlation. We're not going to get into all those in this book. That's why you need a good stats course to really go thoroughly through all those. Rather, we're just going to cover the most common one for each one of these cases. So if they're both numeric, the effect size statistic is a Pearson correlation that we'll go with. We're also going to plot the regression line, but the visualization we'll use is a scatter plot. Again, there's many options for these visualizations too, but we're just going to cover the most common here. If the feature is categorical and the label is numeric, then we're going to use a one-way ANOVA. And also, we'll use some students' t-tests for individual comparisons, and we'll get into that later. But the visualization in this case is going to be a bar chart. We have categories or groups represented by the bars across the x-axis, and then the label or the y variable is represented by the height of the bar with some sort of average or count or other statistic or something like that, which is numeric. Lastly, if both the feature and the label are categorical, so a good example here would be there's a lending club data set, and the status of a loan could be current, it could be late 30 days, it could be fully paid, it could be charged off. There is some ordering to those groups, but it's difficult. But we would look at something like income verification. So was their income verified? Was it source verified? Did we call the employer, or did we just take their word for it? These are different groups or types of income verification. If we want to see if there's a relationship between whether or not or how they verified their income and what the current status is of their loan, those are both categorical. We'd use a Pearson chi-square. And the visualization here, it's a crosstab, which is really a table, but we can overlay a heat map on top of that to make it a bit easier to visualize. Now, maybe my example right there wasn't perfect because as I think about it, both that label and the feature are actually ordinal, but ordinal is a special case where sometimes we analyze it as categorical features, meaning we lose the order, and other times we analyze them as numeric features and we maintain the order. And we'll talk about that more later in the book. We kind of have to try it both ways to see which one is better. But for now, let's go on with the numeric to numeric situation here. So again, I'm going to assume that you have some background in stats if you've taken this class. If not, it's not hard to get up to date on these. Pearson correlation has certain assumptions, and we talked about some of those in the prior section. It assumes that there's a normal distribution with each of the numeric features. It assumes, well, let's proceed with the formula, and then we'll talk more about those a bit later. So this is not something that I'm going to make you memorize. Your instructor might talk to them, but I don't for my students in this book, but it's here more for your reference. The idea is to see and collect the distance between, here's the difference between runs times the difference between rises of the observed versus the mean. I shouldn't say difference between two because it's we sum those up and then we divide by this square root of squared differences. And basically this gives us a single score that ranges from -1 to 1. And here is an example of 3 scatter plots with perfect correlations. So notice the slope of the line isn't necessary for the correlation to be perfect. Oh, and actually that R is wrong. I just noticed that right now. Anyway, right here, this correlation is 1. That means each dot lines up perfectly with each other. There's no variance whatsoever. In other words, a unit change in X is perfectly related to a unit change in Y. It doesn't matter what that change is, but it's every single case fits that unit change every time. So in this case, I see that -1 is incorrect. This is a correlation of 1, but notice the slope is 0.5, whereas this slope is 1. So even though we commonly show correlations with our linear regression function in a scatter plot, these two are not necessarily related directly. Here's an example of a correlation of -1. This is correct. This line goes down, meaning a unit change in X leads to a reduced change in Y. But again, it's the same all the way. Here's an example of where the correlations are a bit closer to 0. So here you see the dots are spread out a bit. However, they're still they're really closely grouped around this line. You might look at that visually and think, no, there's a lot of spread. Well, actually, a correlation of 0.91 is really, really high. And it's rare we find something like this unless we're looking at something that is, almost a direct reflection of the other, kind of like year that you were born with your age on the Y. It's not perfectly correlated because it depends on what month you were born in too, but that would be an example where we'd see a really high correlation like that. And then here's a similar negative version. You may have also noticed, again, our linear regression equation up here. This is our y equals mx plus b, m being our slope, so this means a unit increase in x has the same unit increase in y, 1 over 1. This one, -83, means it is a 1 unit change in x leads to -0.83 change in y. And then, of course, 3.2, that's where it crosses the y-axis, 46.5 right there. So let's go to something even more spread out. Here, you might, if you didn't have these lines in the charts, you might look at that chart and say, I don't see any trend at all. It looks to me like those dots are randomly scattered. However, the actual correlation is still really high, 0.42. That's unique. Or not, sorry, no, it's not unique. That's an example of how sometimes visually it can be a bit deceiving. So we really need both. We need a scatter plot visualization as well as the correlation to really understand what's going on. So why do we visualize it at all if it's so hard to, if we can get such a high correlation and it doesn't seem to match up here? Well, let me go back to the assumptions chapter and show you why. The reason why we want to visualize a scatter plot every time is to check for certain assumptions, and one of those is the assumption of linearity. So I don't know if you remember in the video in this section I said hang on or hang tight with these other assumptions. We're going to come back to them later. This is the time. So look at this scatter plot right here. Clearly, the line that fits this data the best is not a straight line. And you can see that by looking at the scatter plot. If you just calculated a correlation, you would never have known that. And in fact, if you drew a straight line through this, that correlation is still going to be really high. It's going to go straight like that, but you wouldn't know. I mean, you just get a score back for the correlation, like 0.7. You wouldn't realize that actually, in fact, there's definitely this clear curvilinear relationship with 2 inflection points. Same thing down here. Clearly, it goes up, but then goes back down again. You would never know that if you didn't look at the scatter plot. So that's why we never do just one or the other. We never just calculate statistics or just look at visualizations, because there's things we miss in both cases. If we don't have the visualization, we miss that this assumption of linearity is a bad assumption, meaning that there's something other than a straight line that'll fit it. If we only look at the scatter plot, then we could make the mistake of thinking that, hey, these dots this is a very small correlation, when in fact, no, 0.42 is a pretty big correlation. So what is a good and what is a bad correlation? Well, there's lots of opinions, and this isn't a hard and fast rule. However, Cohen's standard, Cohen, you'll hear this name a lot if you get into statistics. There's certain names, Tukey, Cohen, that you hear all the time. These are some of the early founders of statistics. But anyway, what he said was that a small effect size is something between 0.1, 0.29, medium 0.3 to 0.49, and then large 0.5 and above. These are correlations here. In my experience, most of our effect sizes are small. That doesn't mean they're not useful. Remember, if you haven't heard this story before or read it earlier in the book, there's a classic case of Netflix where they gave their prize, had a prize for, they gave away $1 million, and they started paying out on this $1 million to anyone who could take their data and improve their prediction of what movie someone wants to watch next by 1% or better. Okay, this is 10% to 29%. Well, not exactly. This is correlation, not R-squared, but it's related. So only a 1% increase was worth $1 million to them. And so if you get small effect sizes, do not think, oh, well, I've got bad data, this isn't going to be useful. No, I have found a lot of value in correlations around 0.1. So anyway, let's go back to our assumptions one more time here. So how do we test for this to see if there's a curvilinear relationship? All right, well, let's start with plotting a scatter plot. All right, let's pull up some data. This is our histogram data. Let's start a new one here. And let's plot age against charges. All right, so remember, we always have to disaggregate when we first pull that in there. All right, this is one of my favorite charts because it really highlights this point. So here we have age across the bottom. As people get older, their charges for insurance goes up. Why does it start right here? Well, our data set, we don't give insurance plans to customers who are younger than 18. Otherwise, they're part of their parents' plan. So 18 is the beginning of our data. But look at this. We've got 3 very distinct different groups. We're going to explore this and dive in a bit more detail here. But what we can do is pull in a trend line. So let's drop this in. So switch from data here to analytics. Click on trend line and drag. So remember, click and drag. Don't just click and then click again. But click and drag. And look, we've got several options for trend lines. Let's start with this linear one right here. So here's where it draws the line. Why is it way down here when a lot of the data appears to be up here? Well, look, this data is very dense. And so the sum of squared residuals is still going to be closer to this area where the data is very dense. So clearly we have these people this group right here, who seems to do the bare minimum each year as they go along, and maybe just regular checkups, and that's it. Then we have a group that seems to need a bit more help, and then a group up here that seems to need a lot of help, have some serious problems. How do we know that this straight line is the best? Well, here's what I do, or what we do. Hover over that line and look and see what pops up. We get that charges equals 257.723 times age plus 3,165. That's our linear regression equation for the line. That tells us the slope is 257.725, and it crosses the y-axis at 3,100. And you can see that over here, that line that's right about 31 or 3.1K. Now, look at that R squared. R squared is called the coefficient of determination. In a linear regression with just 2 variables, it is the literal equivalent of squaring correlation, of R squared. And what it represents is the variance in the y explained by x. So this tells us that 8.94% of charges, 8.9% of the variance in charges is explained by the variance in x. So a 1 unit increase in x can predict a 1 unit increase in charges 8.9% of the time. So the equivalent of that in a correlation, well, what's the square root of 0.89, let's see here. So the correlation for that one would be 0.0894. I'm doing this on my calculator on my phone here. Square root. No, that's squared. Where's square root? There it is. All right, that's almost a 30%, the 0.3 correlation, which makes it a medium effect size. That's really, really good, actually, in my opinion. And then we get this p-value below that. So I'm going to assume that you've had some experience in stats. The p-value represents the likelihood that this correlation right here, this r squared, this linear regression equation, all of these stats, it's the likelihood that we got those just due to chance, by pure luck. In other words, because that likelihood is small, we can interpret this that there is a correlation between age and charges of about 30%, and the r squared is almost 9%, and that this is what the relationship looks like. So the smaller the p-value is, the more likely we assume that this relationship or this effect size we found is true, and that we'll get it again with a new data set if we collect it. So it's kind of like a double negative. It's the likelihood that that this relationship is not accurate, meaning there is a relationship. Anyway, so what do we do to find out if the assumption of linearity is true? Well, what we do is we come back here to trend line, and we grab it again, and let's try out these other options. See how they all allow for different mathematical versions? So logarithmic says, let's take the value of age, and let's create a natural log version of it. And a natural log has a diminishing return. So if we go over here to data source, look what just happened here. Oh, actually, no, it doesn't make that for us, but we can create one. Let me create a calculated field and show you exactly what happens here. Can I do it from right here? Will it let me? No, I'm going to have to go back to my sheet 5 here. I'm going to call this, I'm just going to call it age scatter, and we're going to assume that it's on charges because we've decided that that's our label. And I'm going to come here and create a new calculated field, and this is going to be age ln. Now notice Tableau has already created this field in memory in order to make this line, but we're going to explicitly create it so you can see exactly how that works. And we're going to say this is going to equal the ln natural log of age. There we go, this equation is valid, apply, OK. Go back to our data source and look at what it's done. It's taken every value of age right here, and it's taken the natural log of that. So natural log takes large numbers and makes them a lot smaller, and the larger the number, the smaller it'll make it, resulting in this diminishing return. So as x gets higher, it reduces it more and more and more. So it eliminates, if the scatter has this diminishing effect, then a natural log line will fit it best. So let's take a look at the function. Look at what it's done there. It said, all right, 8,900, 8954 times not age, but the natural log of age. And then, of course, now our y-intercept is negative. It gives us an r squared of 0.084. Still a very significant p-value, but that r squared, is that bigger or smaller than the r squared of our linear equation? Well, if you remember, the linear one was 0.089, which means this is smaller, which means this line fits the data worse than a straight line. So far, our assumption of linearity is holding true, and we like it. And we think that we're okay, even though we've got these three groups. So let's go and try another one. Let's go back to analytics, grab a trend line, pull this in, go to exponential, which is the reverse here of a logarithmic. It gets higher and higher. Well, no, sorry, this is an e raised to the age. So exponent. Yeah, basically the reverse of a log. So what this does here, let's hover over it and see. Look at that r squared, 0.2786. That is much bigger. Okay, so this tells me that no, the assumption of linearity is not good. Rather than using, and that doesn't mean that we can't analyze our data or that age is a bad variable. It just means that the version of age we should be using is e raised to the age. And actually look at that formula. It's e raised to the 0.03451 times age. So we can recreate that formula here in our data. In fact, let's do that. So I'm just going to look at that number and remember it, 0.03455. Go back to our data here, and I'm going to change age ln because we know that's not what we want. And I'm going to call it age, or I'll call it age e for exponent. And we're going to change this to e, or exponent. Oh, there it is, exp. I don't know the Tableau language that well, but usually you can figure it out. It's not too hard. And it's going to be 0.0345451, something like that. I'll double check it, times age. There we go. So we've recreated what that sum of squared, there it is, 0.0345451, perfect. So we're recreating that, and we don't need the slope, we don't need 2308. We just want the formula they're using for age in that linear regression equation. We say OK, age E, and this means that we've now found that this version of age is the one we use to satisfy the assumption of linearity. So again, if a straight line doesn't fit at best, that doesn't mean we have a problem. It just means we need to use a different version of that variable. So let's check a couple more just to be sure. Let's go back to analytics and let's try out trend line. Let's try out polynomial. So polynomial lets us have like squared, cubed, quadratic terms in the equation. So it takes it from a linear regression, a simple linear regression, to a multivariate linear regression, which we'll learn more about later. So see, look at our function there. We have age cubed, an age squared, and then a regular age. So in this case, r squared goes down to 0.09, so we're not going to use it. It is better than the straight line, but not better than our exponent. If this were to be the best one, what I'd have to do is create 3 versions of age, a cubed, a squared, and then keep the original, and I'd need to use all those in my modeling down the road. But for now, since our E version was better, I'm not going to use this one. Let me check the next one. Trend line, power. What does power give us? Power is also very good. This one allows it to be raised to, it sticks with just one term, but it lets us raise it to any power we want to. So instead of squaring it or cubing it and having multiple terms, we still have one term and it's raising it to the 1.259, which actually mimics the exponent, right? Because it's getting this increasing rate. As age gets older, charges increase at an increasing rate. But it's not quite as good as the E was. This one's 0.28, the other one is 0.29. So I'm going to stick with the original, or sorry, not the original, the exponential as my best line. Oh no, actually I was wrong. This one's 0.27. So I take it back. I had remembered wrong. It is the power one that's best. This version right here, 0.28. So let's revise our age to that one right now. So it was raised to the 1.25954. Okay, back here to data. I'm going to edit that, and I'll call it age power 1.25. What was it? Just so I remember. 25954. 5954. All right, so I'm going to change this to, let's see if I can figure out power. Oh, there we go. Number power. So I think that means I want age here. I'm just experimenting. I haven't tried this before. 1.25954. Let's see if that looks right. So each age should be slightly larger than the original value, if that's right. Yep, perfect. Okay, so now age here says 40, but the actual age was 19, 38, 18. That's correct. So this one variable is the version of age we now want to use instead of the original. Now, I'm not going to delete age from my data set. I'll leave it there. We can always easily pull variables out when we get to the modeling phase, but I've now created a better version, and I'm going to make a note of this in my documentation. So here's what we're going to do. Oops, that's not what I meant to do. I'm going to go back to the scatter plot. I'm going to copy this, the image, and copy. Actually, no, let's give this, I'm going to be simple. I'm not going to format my title for now. I'm just going to keep it the way it is. Let's go to our data exploration report, and we're going to begin, I was going to say this, report details the relationship between each potential feature with the label charges. You can add here in this paragraph any other information you want that might be useful. I'm not going to worry about it for now. I'm just going to go ahead and make this heading 2. And for each one of these, I usually start with a quick explanation and hypothesis. We expect, and this is where your domain knowledge comes into play. Let's say that you've worked in insurance before and you have some experience, and you can say, we expect that age will have a positive effect on insurance charges because people tend to have more health problems as they get older. Now, when I've created some of these reports, I've had to justify myself. So what I'll do at times, and I'm not going to ask you to do this for this class, your instructor might, but probably not. What I'll often do is go to Google Scholar and look up some research. And so I'm at, by the way, just so you can see that, I'm at scholar.google.com. Anyway, teaching a sports analytics class right now. That's why it's got that in there. But let's see, age and health cost. And you can find, let's see, benefit and cost analysis in geriatric care, turning age discrimination into health policy. Usually you can find some paper that just simply cites and says, yes, people cost more money as they get older. I can come here, and if this is the one I wanted, I can click on this. And there's my site. It's Avram J 1984. And I can come back here and then say Avram 1984. And then I'll have down at the bottom references. I'll paste in my reference, give that a heading, probably a heading 1. There we go. So sometimes I've been asked to format this as like a hypothesis. In this case, I'd call it H1. And in this case, it's a directional hypothesis. Because I have theory to support that older people cost more money, I'm only going to list this as H1. If I have no theory and I don't know what the relationship should be, actually I'll show you that an example of that in a minute. For now, let's paste our, oops, not that. Let's go back and grab the chart one more time. Copy image, whoops, copy, not there, here. Paste in my image. I really don't need to be that big. I'll make it a bit smaller. And then I'm going to say down here, linear regression equation. I'll go ahead and pull this in from Tableau. Oops. I wish there was an easy way to copy that equation. 96.3325, 96.3325, age raised to the 1.2, what was it again? 1.25954. 5954. I'm going to say that the R squared for that was 0.28. What was that again? 629. I will say 63. That's good enough. Here, the obsessive compulsive part. He's coming out. Raise that up. There we go. And we're going to say correlation R on that. All right, now it didn't give us a correlation, but it did give us the R squared. So there are other ways to get the correlation, but if you just want to quickly, in this case, I would say when I'm going through each individual variable, I don't feel like I need to put the correlation in there. We'll come back and add a correlation matrix later, so I'm going to leave that off, and instead, oops. Instead, I want to add the p-value. That's important for them to see if this regression equation right here is statistically significant. And I just noticed I forgot my, y-intercept. Oh, in this case, it's forced to 0. Wow, either forced to 0, we'll find out, or it just was 0. I doubt that. Yeah, we'll check into that in a bit. So I don't have a y-intercept. Leave that. p-value, we're going to say less than 0.001 and call that good. So in summary, age appears to have a medium effect size on charges that is very reliable. In other words, because the p-value is so small. So, as a summary of where I'm getting all this from, r squared, let me just highlight some of these. I'm going to say a medium positive effect size. So medium because I know my r, oh actually no, the square root of that, it's going to be a large, not medium. If I do the math, 0.2863 square root is actually 0.535. So that is a large effect size. So I'm going to say large and positive. Positive because the slope right here is positive. Effect size, and that's because I'm getting that from my r squared. R squared is probably the best measure of effect size. I mean, r is as well, but more commonly we go with r squared. That is very reliable. Where am I getting that from? Very reliable is from the p-value because it's so small. Okay, so let me add a couple more notes here. Although, actually no, let's say we tested all non-linear transformations and found that a power, I'm going to say raised to like this, raised to the 1.25954, that a power transformation provided a much better r squared value, and that's where we get 0.2863 greater than, before we got 0.089, something like that, I think. You can go back and check if you want to. I'm not going to worry about it. Keep my decimals consistent here. 6, there we go. Much better r squared value. Therefore, we created a new version of age called age power 1.25954 in the data set. So we're almost done. One more thing. We have tested now for the assumption of linearity. However, we have this other assumption we put off down here as well, homoscedasticity. So homoscedasticity is the assumption that the variance in y is consistent over all values of x. Now clearly this is one example of where that's not true. We have here what's called heteroscedasticity. Wide variance on the ends, little variance in the middle. Same thing down here, it starts to flare out into this cone shape. So why is this a problem? Well, it's a problem because our linear regression equation gives us a prediction that we assume is going to be similarly accurate over all values of x. So for example, now this line I allowed it to inflect here. However, let's say this was a straight, well, it doesn't matter. Let's say we got the value of 0 for x. If we go up to y here, we would predict, well, y would be a 0 then as well. And that is really reliable. So we find out that whatever this represents, the true value was in fact 0, so we're feeling really good about our prediction. So somebody else comes in with a value of 4. All right, let's say this is Lending Club, and we're trying to predict who's going to pay off their loan, and this is their total liabilities, net liabilities and assets. So someone who has equally as many assets as they do liabilities, we're able to very reliably predict whether or not they'll pay off their loan. But we come over here and we find this person then who has much more assets than liabilities, and we think, oh yeah, we're super confident. We've been right every time here, so we make a prediction over here at 4, and we find out, so our prediction at 4 is right where the line is, right here, but we find out in fact that they're down here and we had to charge off their loan or something like that. So it makes us overconfident in some places and underconfident in others. The overall R-squared for this is going to be something in between this flared out part and this highly reliable part. So the reason why this is an important assumption is because we need to understand where our values, where our predictions are going to be more or less reliable. So how do we test this? Well, I'm not going to go into that in this video. I'll provide another video right below this one, or back in this section. Actually, I think I did. Back in this section that shows you how to go through and test for what's called White's test, and where are they listed at? White's test and the Bruce-Pagan test. And you can get a statistic that tells you just how much heteroscedasticity you have. But for this class, I'm going to keep it simple, and I'm going to make that optional. Talk to your instructor for sure, but really all I want you to do is to create a scatter plot and look at it. And you can easily tell that there's a problem here and that there's a problem there. So what I'm going to do is go back to Tableau and say, okay, let me go back to age here. Is the scatter different across all values of x for age? Well, no, it's not. It's actually consistent. There's a consistent grouping here and up here, but it appears to be the same across all values. So technically, I don't have a problem with heteroscedasticity either. So I'm going to come back into my report and add that, and I'm going to say, looking at the scatter plot, there appears to be a consistent variance in charges for all values of age. However, and this is an important however, so I've tested for all my assumptions, but clearly we have an issue here. So I'm going to put in a big however, and this is an important one. I'm going to bold it, highlight it, make sure that people who read my report see this. However, the scatter plot clearly reveals that there are three distinct groupings of customers and I'll say most cost very little, relatively speaking, but there are two groups who consistently, and that's the important part, consistently, and that's why we have no issues with heteroscedasticity, who consistently cost more. So the solution here is to do some clustering a bit later on. Well, one solution is, but we'll get to that a bit later. But it's important to know that this is why we have to generate a visualization. None of the statistics that we have to test for assumptions have revealed this problem if we hadn't looked at it for ourselves. So that's why data exploration, or the data understanding phase, involves both a visualization for each feature label pair, as well as the relevant statistics, as well as a short write-up to explain what we found. So we can also summarize these later in a table. For now, I'm going to create another chart like I have here for BMI. So go ahead and make a new worksheet. Let's call it BMI scatter. And I want you to put in BMI here, charges up here for the X and the Y. And I want you to go ahead and start dropping in some trend lines. So linear trend line, notice we get p-value, very low p-value. So this trend line right here is reliable, but the R-squared's only 0.39, almost 4%. So we go through and try logarithmic. That gets worse, 0.017%. Okay, no problem. Try exponential. Back up to 0.039 again, similar to the straight line. It's not much of an improvement. Then let's try polynomial. Okay, that gets much better, 0.068, at least compared to the straight line. And then power, yeah, we can tell that's getting worse, 0.09. So let's go back to our polynomial again. So when the polynomial is the best one, it's kind of tedious to go through and look at this and copy that whole regression equation into another document. So I want to show you something you can do. Right-click on the line, and it's either describe trend line or trend model. Oh, here we go. Perfect. Beautiful. This is everything we need. So I'm going to copy all of this out of here. Well, I guess I should copy the image first to keep it consistent, but that's okay. And let's come in here and let's create our entry for BMI. I'm going to make this a heading 2. Let's give another line break right there. I'm going to come down here and paste this. I don't want that to be Times New Roman. Go back to Calibri. What is this, 11? All right, let's make that 11 as well. Then keep it consistent. Okay. Equation, I should probably keep things consistent. I don't have the r squared on here, do I? I need to add that. So let me go back to Tableau. I can either get it just by looking at this here, or I think I get more details if I go to Describe Trend Model. Yeah, here we go. R squared's already in there, including standard error. We haven't talked about that, but I'm going to save that more for later in the book. This is a little more than we need for what we're doing right now, but so I'll just look at R squared and say, okay, I'll grab that, copy, and let's go back here, and I'll say, I'll just add it down here, R squared, tab over. I can tell that this is in a table format because it's added that in there. I'd probably go back in later and put this in the same order and format as this one down here. But here's what I get. Coefficients, I get my full equation, but it gives me an individual p-value for each one of my coefficients, each one of the items in my linear regression up here. So by themselves, you can see that each individual element here is not significant, but the overall model based on this intercept, my p-value is very significant. So that's okay. What this means, I'm still going to keep, I'm going to make a version of all of these to keep in there. So I'm going to have a version, I'm going to leave chart, actually what it's done is it's changed charges. So what I need to do, I don't want it to modify the label in a way that it creates 3 different versions of it. Rather than predict BMI from charges, I want to predict charges from BMI, and Tableau just didn't, oh, here's my problem. I put them in the wrong spots. Okay, sorry to, you know what, I'm going to leave this mistake in the video because I want you to see what'll happen if you do the same. So if you run into this, I just want you to see and make sure this doesn't happen to you. I'm going to come up here and switch these. Okay, and notice it changed my regression equation a lot, and instead now I have charges equals BMI. That's what I wanted instead. Let me double check. Look how r squared has changed. Let me double check and see that I haven't, that there may not be a better version of this trend line again. So let me go back and just try them all again. So 0.0393, 0.0397, that's a little better. Exponential, 0.01, that's worse. Polynomial, 0.041, that's still the best, but not quite as good as it was before. And that means I think power is going to be worse too. So, yep, so we're still going to stick with our polynomial, but that has changed things a bit for us. I'm going to grab this one more time. Let's do that. Yep, Control A, Control C. Oh, there's a copy button. I guess I could just use that. Let's paste that over all of this again. And I'm going to add in my r squared again. And in this case, it's 0.04, what was it again? 4137. I'll call that good enough. And I'm going to change all this again to Calibri 11. And now let's come in here and put in, we expect that BMI, actually I'm going to stick with formally hypothesizing these things. Same thing up here with this one. This isn't the way you would state a hypothesis. It's just letting know that we have a direction we expect things in. When we formally state hypotheses, it's usually a bit more succinct than that, but I'm going to call this okay. We expect that BMI will have a significant positive effect on charges because it is well documented that healthy weight leads to better health and thus lower healthcare charges. And again, you could put a citation in there if you wanted to. If you're doing this for my class, I'm not going to make you look up a site. Don't worry about that. I just wanted you to see the way I've done it in the past. And now we just need the visualization. Copy, image, whoops, copy, and paste. All right, that's plenty big. It just lets them see what the trend is. And here, we do have a heteroscedasticity problem. I can see that here. It looks like that BMIs that get higher have a group up here that gets really high, but that's not everybody. Look, the vast majority of people with higher BMIs still stay low, or at least the same as everybody else. So just having a higher BMI doesn't necessarily mean you're going to have higher charges. So what I learned from this is clearly there's not one variable that tells the whole story. Age is not telling what's going on with these three groups. BMI starts to help, but there's still two different groups. I need to be able to look at both of them at once. So you know what I'm going to do? I'm going to create a 3D scatter plot. But before we get there, I want you to pause, and I want you to create the last one for a numeric feature. We have one more, children. So I want you to pause the video and see if you can remember all the steps. Do it without watching the video if you can, and recreate everything above for the children variable, and then come on back. All right, let me show you what I've done here. So a couple things. I went ahead and I forgot back in BMI, I called that one H2 since we already had an H1. So hypothesis 1 was concerning age. Hypothesis 2 is BMI. Down here for children, though, I could not think of a reasonable explanation for why there is a relationship between children and charges. So I discussed a few different things. If someone comes in with existing children, that could mean they're more likely to have more children. Therefore, you could say that children lead to greater charges. Or you could say that children cause greater stress and anxiety, which leads to greater health costs. However, children could also offset those costs by providing a reason for parents to stay healthy so they can be available to support and nurture raise their children. So, therefore, the relationship between children and charges is rather exploratory, meaning we don't have a directional hypothesis. So we can't say that we know that it'll cause more or less. We're just exploring. So in that case, when it comes to hypotheses, I'll usually say, I'll list out two versions of the same one, H3. This is the null hypothesis, there are no charges, and the alternative hypothesis, the null is there's no relationship. The alternative is there is a relationship. So that's how I list that. Again, talk to your instructor if they want you to actually include these hypotheses or not, or what. What I did find was that there is a linear natural log effect. So there is a logarithmic effect between children and charges. So let me show you what I mean here. R squared, 0.026. That's a rather small R squared. And to get that, it wants us to take the natural log of charges. Now the problem is my other transformations have kept charges the same. We didn't make a change on those, so I can't very well make an adjustment for linearity with one that keeps the same label, and for others that doesn't. So I could do a couple things here. I could go back. It may be, first of all, that we're going to want to make a natural log adjustment to charges down the road anyway. However, I don't want to cover that quite yet. What I want to do instead is simply say, all right, if we flip this around, even though it's reversed, do we still get a good R squared, and does it change the adjustment? Oh, whoops, let me go back here. So here we go. I think, did I copy it wrong? Format, no, describe trend line. This version, there we go. This version took the natural log of charges. Well, the reverse of that is the exponent of children. So I just wanted to point out here that for some reason, Tableau gives us the inverse version here in the describe trend line part than what we're getting right here. So you notice this one, it's E raised to the children. and in the other one, it's converting the charges to natural log. So let's see if we get a different version of the described trend model. No, it doesn't give us exactly what I'm looking for here. So what I'm going to have to do is just go back and eyeball it. So we want 7815. I'm going to take this off and say point, no, not point, 7815.88 times E raised to 123064 times children. Perfect. There we go. And then that leaves r squared at 0.026. 0.026. There we go. Now, 2.6% r squared, that is a correlation that's in the small range. What's the square root of that? Let's see, 0.026 square root is 0.16. So it's a decent size, that correlation. It's small, but still very useful. Down here we can see the significant impact of the coefficient for children. That's this right here, and the intercept. So what I put here is that there appears to be a significant positive effect of children on insurance charges. This relationship is not linear and requires an exponential transformation of children. However, we cannot determine the exact reason or nature without exploring greater detail on the specific charges. So in other words, we don't know why children are leading to a higher effect. However, given that the effect size is relatively small compared to other features, we do not feel that this is worth exploring yet. So we won't worry about it for right now. All right, I think I forgot in our last video to put a write-up down here for BMI. So recall BMI. I'm going to add something down here at the bottom and say there is a significant positive effect of BMI on charges. However, the relationship, is not linear, is not perfectly linear, and is better modeled with a cubed and squared term. In addition, I want to talk about the heteroscedasticity. In addition, there appears to be an issue with heteroscedasticity in that some customers with higher BMIs clearly cost more, while the greater majority do not. So what that tells me is that there's possibly something interacting with BMI that's leading these customers to cost more, while a lot of them, most of them, seem not to. When I say most, I'm just saying that it appears these dots are more dense down here at the same values of X than these up here at those same values of X. So we need to make a couple more additions to our data set. So what we're going to do is go back to Tableau, and let's create one for both of those. Let's go to data sort. No, actually, no, back where we were was fine. On BMI, let's make a new calculated field. So BMI is where we've got the polynomial term with a squared and a cubed term. What we do there is we're going to make one that is BMI squared, not BNMI. And this is simply going to be BMI. I think we can just do it this way, times BMI. Okay. And then let's make a cubed version 2. Create calculated field, BMI cubed. I bet there's, yeah, power. Let's do that. BMI, so it wants the number first, BMI, and then we'll put in 3. We could have done the same thing with the squared. Let's take a look at our data source, make sure those look right. So BMI over here is 27. Yep, 778 is that squared and that cubed. Perfect. So we've made the nonlinear adjustments for age and BMI. Let's make the one now for children. So for children, it was 1.23064. Again, we don't worry about this coefficient right here. We don't worry about the slope. We just want to do this one. So it's going to be e raised to the 0.123064 times children. Okay, great calculated field. This is children exponent 0.123064. And here I'll just say exp children, but actually I'm going to say that times children. There we go. Okay, take a look at it, make sure it looks right. Let's see, these exponents of 1 are, oh yeah, for 0 children. That makes sense, yep. Okay, I think we have taken care of all the numeric ones. Let's end this video before going on to categorical to numeric.